Okay, let us resume our discussion on the interrupts that we have been having in this session today. Now, let me also mention a little bit more about these interrupts. As we have seen, interrupts can be classified like maskable interrupts or non-maskable. We have seen that on our MSP430 we have both varieties. There is one more way to classify interrupts, and that deals with vectored and non-vectored. What is the meaning? When I use the term vectored interrupts, that means whenever an interrupt happens, I know exactly where to go looking for the subroutine to deal with that interrupt. I can also have non-vectored interrupts, which means, well, an interrupt has happened, but I exactly do not know where to go, and therefore, the system must provide me some information to help me locate the subroutine to handle this non-vectored interrupt. Well, MSP430, most of the interrupts are vectored interrupts, all the interrupts are vectored interrupts. The source of the interrupt also supplies the address. In fact, this address is available in the memory map of MSP430. The top, that is the highest memory locations, are reserved for storing vectors for each of the interrupt sources. Also, now imagine that at a given time when the microcontroller is ready to branch off for executing a interrupt subroutine, what if two interrupts happen at the same time? Of course, microcontroller cannot go to satisfy the needs of both the interrupt sources at the same time. So, it must prioritize, and this is called what is the interrupt priority, which means the one with, if two events happen, the one with higher priority will be serviced first. After the completion of that interrupt, you can go and execute a subroutine for the second interrupt. The reset vector, and we will see how this is prioritized in MSP430, the higher vector address means a higher priority, and so reset vector has the highest priority. Why? Because it is located at this address, and just to repeat, the address is of two addresses, that is your instruction is at F F F E and F F F F, all right. So, you are going to, so the vector at this address will have the highest priority, the one after that will be F F F C and F F F D would be the lower priority interrupt compared to this, and so on. Here is the clipping from the MSP430 data sheet, which lists all the interrupts, what are their names, the source, and what is the flag referring to the interrupt flag that we mentioned, and what is the address of the vector for that interrupt, and what is the priority. Of course, as I mentioned, 31 highest priority is for reset, and as you go down the priority decreases, which means if two interrupts happen, the one with higher priority will be serviced first. And as you see, the sources of interrupts are a power up condition, external reset, that is a user pressing the reset button, or a non-maskable interrupt, or a timer, here comparators, watchdog timers, another timer, the serial communication protocols, the ADC, and last but not the least, the 2 ports that we have on MSP430G2553. In fact, you would remember that MSP430G2553 is actually available in several physical footprints. The one which we have on our lunch box is in a DIP format. It has 2 ports, but if the MSP430 is chosen to be of the SMD version, it has 3 ports, port 1, port 2 and port 3. But Port 3 does not have any interrupt capability. The only interrupt capability you have for this microcontroller number is for port 1 and port 2. And as you see, port 1 has the lowest priority in this, and also here you see these are all maskable interrupts and only the NMI interrupt is non-maskable. So, let us proceed further. Now, as I mentioned, an interrupt flag is an important element in the whole process of an interrupt being generated, being recognized and being serviced. And the interrupt flag, once it is generated, it will automatically vector to a address location, and usually it will have a single source, but there are peripherals where a single vector is going to help you generate sources from several pins. For example, port 1 or port 2. Each of these ports, as you know, has 8 pins, and each of the 8 pins can generate an interrupt. But if the pin refers to port 1, all the 8 pins will have a single vector. So, it will take you to the same location, and it will have to execute the same subroutine at that location. In that subroutine, you will have to identify which was of all the 8 pins which caused the interrupt, right. So, we will deal with this. Okay. So, when you are ready to incorporate interrupts in your system, in your programming, in your embedded system, there are a few things that you have to keep in mind. You must keep the interrupt subroutine very short, and one of the ways to ensure that is to not use any delay subroutine in your interrupt function, in your interrupt subroutine. Why? When you take too long in that interrupt subroutine, what are you doing is you are constraining the rest of the execution of the main program, or you are starving other sources of interrupts. You want to give all the sources of interrupts a fair chance, fair participation, therefore, you must keep the interrupt subroutine very short. Now, what if you want to actually execute a bigger program? The way to deal with that is to interact, deal with the requirement in the main program, not in the interrupt subroutine. When you are executing an interrupt subroutine, by default all the other maskable interrupts are disabled. That is the meaning. Therefore, you must keep the execution of the current interrupt subroutine to a shortest possible program length, so that you can quickly finish it. When you go back, it will enable the interrupts, so that other interrupt sources could get a chance. Now, for interrupt to be accepted, there are several conditions that have to be satisfied. The first is that because interrupts are often generated from external sources, which means they are asynchronous to the execution of the program on the microcontroller, it does not mean the moment an interrupt is generated, the microcontroller would suspend whatever it is doing and will rush off to execute the subroutine for that interrupt. At the very least, it will complete the current program, current instruction. If it has started fetching that instruction, it will complete it, and as you know, the length of these instructions could take 1 clock cycle or it could take 6 clock cycles. So, if in the first clock cycle an interrupt event happens, it will have to wait till the 6 clock cycles associated with the current instruction are completed. Also, once the interrupt is recognized, if there was no interrupt, the microcontroller would have gone to the next location to fetch the next instruction and execute it. But now, because interrupt has happened, it must store the value of the program counter somewhere, and this somewhere is a location, is a memory location in the RAM, and we call this memory location special region in that RAM, we call it stack. And so, the microcontroller saves the value of the program counter on the stack. Then, apart from the program counter, the state of the microcontroller is reflected in the status register. Even this is saved on the stack, so that when you resume your interrupted program, you can resume with the state which you had before the interrupt happened. Now, if multiple interrupts have happened, it would prioritize and it would give the highest priority to the higher priority interrupt and execute an instruction subroutines related to that interrupt. The interrupt flag resets automatically on single source flags, meaning if there is a source of interrupt which is not shared with other resources, the moment the interrupt is recognized, it will reset this flag. So that next time another event happens on that resource, it can be captured. It also clears the status register within the interrupt subroutine. So, when you enter the interrupt subroutine, the status register reflecting from the main program is saved on the stack, and within the interrupt subroutine you get a clean status register, all the bits are reset to 0, and this will allow you to actually exit low power modes. The GI, that is the global interrupt bit, which is like the global switch, is also cleared, and further interrupts are disabled, which means when you are in the interrupt subroutine, if any other interrupt happens, it is going to have to wait. Once these conditions are all met, then before you go into the subroutine, the interrupt vector is loaded on the program counter, and from there the microcontroller starts fetching and executing the instructions of that subroutine. To help come back to the main program, so this is a reflection of what would be the state of the RAM. So, let us say before the interrupt happened, the the stack pointer was pointing to this address, and whenever the interrupt happens, it has to store two contents, two words. One is the program counter and the other is the status register. So, now TOS stands for top of the stack. So, what was top of the stack here is now at this location. 4 memory locations are used to store the these two registers, the program counter and the status register. Now, once you are inside the interrupt subroutine and you have executed the program, you would do the same things that you did while getting into the interrupt subroutine in the reverse order. The status register of the previous setting will be popped from the stack, which means when you had been interrupted in the main program, the status register was saved on the stack, it will be recovered, and the program counter is also recovered from the stack, that value put in the program counter register, so that you can resume executing the program which got interrupted, which got suspended, that we call as the main program. So, this is shown here. Now, for handling interrupts, for purpose of illustration here, we are going to use the input output pins, and so we are going to look at all the registers which help manipulate, which help control, or which help handle all the interrupts associated with the GPIO, general purpose input output pins. And we have 3 registers which help us manage the interrupts associated with the input output pins. All these registers are 8 bit width. We have an interrupt enable register called PXIE. X here refers to which port we are talking of. For example, if you are talking of port 1, that register will be P1IE. We have an interrupt edge selection register. Why? Because you could generate an interrupt on the rising edge of a signal on a port pin. You could also generate an interrupt on the falling edge. So, you have to tell the microcontroller, do you want to be interrupted when the signal goes like this, or do you want to be interrupted when the signal goes like this. So, that is indicated to the microcontroller by writing appropriate values into this register called interrupt edge selection register. And the third, the most important register is the interrupt flag register, and for reference I have replicated that previous block diagram of interrupts, so that we can assign or we can locate these registers in this block diagram. So, program interrupt enable register is this part here. Here. So, if you want that a particular interrupt should be enabled, you must enable it in this register. So, it affects this red part. The edge selection and the flag register together are here, and so you must get a 1 in this blue bit. If that is 1 and if this switch which is represented by that red circle, if that switch is closed, then only it would generate an interrupt, provided this master switch, let me color it in a third color, master switch here is also turned on, and that is by a flag called global interrupt enable flag, and it can be enabled in various ways. It can also be disabled, and we will see two methods of controlling this flag in a program subsequently. So, to reiterate, we have 3 registers that we must manipulate so as to handle interrupts on the input output pins of MSP430 microcontroller. Let us proceed forward. Now, P1IE, that is port 1, if I want to talk about port 1, interrupt enable. This is a 8-bit register corresponding to the 8 pins that you have for port 1. If you want to enable interrupt on any of the pins, you must write 0, you must write 1 in that bit. So, let me say draw the 8 bits here. So, this would be your P1IE, this is bit 0, this is bit 7. If I write a 1 here, that means I want interrupt associated with P1.0, port 1 bit 0 to be enabled. Of course, a signal has to be applied to port 1 bit 0 for interrupt to actually happen, but this you are enabling it, and if you want to disable it, you write a 0. So, if I write 0 in the rest, that means I do not want to be interrupted by any signal on any of the pins of port 1 except bit 0. This is the interpretation of port 1 interrupt enable register. Second in the line is the interrupt edge selection register. Like I mentioned, you can generate an interrupt on the rising edge and you can generate an interrupt on a falling edge. You have to tell the microcontroller which edge would you like to generate an interrupt, and again here there are 8 bits. And here I am going to write the name of the register. This one is P1IES, interrupt edge selection. If I write a 1 here, that means it will generate an interrupt when there is a transition from high to low. So, 1 means high to low. So, a falling edge will generate an interrupt if you have written a 1 in that corresponding bit. If you write 0, that means you want an interrupt on the rising edge. So, depending upon your requirement, depending upon the state of the logic on that particular pin, you can write a 1 or a 0. Corresponding bit in the previous register, interrupt enable register, has to be 1, otherwise writing a 1 or 0 here makes no sense whatsoever. And the third is interrupt flag register. This flag register, when if it becomes 1, that it will become 1 upon which condition, that you have enabled the register and an external signal which is qualified by the edge selection register has been received, then and then only a particular bit in this register will be set to 1, and if that bit is set to 1, subject to other conditions being met, it will lead to an interrupt. So, let me again show it here. So, if this is P1IFG, if this bit is 1, that means an interrupt on port 1 bit 0 has been recognized, and if the global interrupt enable bit is enabled, this will fly. It will interrupt the CPU and the CPU will go to the interrupt vector associated with port 1, and from there it will execute the subroutine and you can do whatever you want within that subroutine. That is the meaning of this. Of course, these bits can also be set or reset in by software by writing a 1 or 0, and this will generate a software controlled interrupt. That is the meaning. Normally you do not want to do that, but that is also possible. So, let us see what is the flow of the program when we are dealing with interrupts. This is very important. Now, in C, how do you tell the program when you are writing a program in C language, how do you tell the compiler that this subroutine that you are writing is for the purpose of handling a particular interrupt, and you do that by using a hash declaration called hash pragma. This is a keyword vector. You are telling that you are going to deal with timer 0 A0 vector, and what program to be executed in response to this vector, this is the name of the program. So, you this is by the way double this interrupt void, these are all necessary, you cannot change these. This is your choice, this name is your choice, you can put your own name. So, you have to have a hash pragma name given, then this is a keyword here, and the name itself, the name of the subroutine is your choice, you can put whatever you want. Of course, it should not be a reserved keyword or anything else, this is required. Once you write this in your C program, you must thereafter write the subroutine associated with this label. Now, void here means you are not passing any parameter to the subroutine, nor is it passing any result back to you. Then how does the interrupt program help you? Through way of shared memory locations, all right, variables. So, we will see how that is handled. Now, I have put together this list from the MSP430 header file, so that you know what are the names for each of the vectors, like for timer 0 what is the vector and so on. So, here is the, as you can see, this is the vector for trap, that is the non-maskable interrupt. No, this is not the non-maskable interrupt, it should come here somewhere. So, this is a trap vector. Then you have port 1 vector, that is the vector you would go to when there is an interrupt on port 1, here it is for port 2 and so on. So, in your C program you must use these exact names in capitals to enable you to link your interrupt subroutine for that particular peripheral. We will illustrate it with an example. Now, what do you do? What happens in an interrupt subroutine? Well, the moment the main program is interrupted, you must save the context, and what do I mean by the context? Context is reflected by two things, the status register plus the program counter. So, both these registers have to be saved, so that you can resume using the values here whatever program was interrupted. So, this must be saved, and this is done automatically by the microcontroller. How? It saves these two registers on the stack. Now, once you enter an interrupt subroutine, the global interrupt enable bit is turned off, which means no interrupts can happen during the execution of this program, but you as a programmer and a designer are free to enable the interrupts, which is what we are saying here. It is possible to enable interrupts within the interrupt subroutine, and I would request you, I would advise you to exercise great caution in trying to re-enable interrupts within the interrupt subroutine. Of course, what after that would come is the actual program that you would execute in the subroutine. Now, if the source of an interrupt had multiple sources, it is your responsibility, that is the responsibility of the program to reset the flag, so that subsequent setting of the flag will generate another interrupt, and once that is done, you can restore the system context and return, meaning When you return, automatically the system will recover the stack register, the status register and the program counter from the stack and put it into the respective registers, that is status register and the program counter, which means you will go back to the main program which had been interrupted and you will resume your execution from that point onwards. So, this is the way things happen in an interrupt subroutine. Now, as I mentioned, how does an interrupt handle variables? How does it communicate with the main program? It is not that an interrupt happens, you go into an interrupt subroutine, you do something there and you come back. No, oftentimes you would want to convey to the main program that an interrupt happened and this is the input provided, and that is done by using variables. But these variables are not normal variables, they have to be declared as volatile, and volatile is a keyword. So, you have to append this name volatile in front of any variable. What it does is, oftentimes the C compiler will keep a copy of variables in registers, because reading anything from a register happens quickly. But if the main variable is in the memory, you may not get its exact value. But by using this keyword, you are telling the compiler, please do not use a copy of that value, go into the memory which is been reserved for that variable, fetch the value from there and then pass it. And as a rule of thumb, all the variables associated with ports and interrupts should be declared as volatile, and we will see that example either in this or subsequent lectures. So, here is a checklist of things that you must perform in the main program, so that interrupts can happen if they happen, and if they happen they can be serviced. You must have enabled interrupts both in the module and the global interrupt enable bit. You must have interrupt subroutine for each of the enabled interrupts. You must acknowledge that interrupt, meaning you must disable the flag within the interrupt subroutine, and if you are using any variables, you have to ensure that they are declared as volatile. Now, what we are going to do is we are going to illustrate how you can experiment with interrupts on your MSP430 lunchbox. So, in the first exercise, we are going to connect the lunchbox to our laptop, and we will discuss this code. We will download this code on the lunchbox, and using the peripherals on the lunchbox itself, we will see how interrupts can be generated and how they can be serviced, that is how an interrupt subroutine can be executed in response to an interrupt being generated on the lunchbox. So, take out your lunchbox and connect it to your laptop, and let us go to the through the code so that you understand how the code works and how you can modify it. So, in the first exercise, we are going to use the switch on the lunchbox as well as the LED on the lunchbox to illustrate this interrupt being generated by the switch. So, as you know, on the lunchbox there is a switch connected to bit 3, that is P 1.3. You know that that is the a switch connected to this. You also know that this switch is connected in the pull up mode, meaning there is a resistor and a switch like this. The switch is grounded on the other side. This side of the pull up resistor is connected to VCC, and this junction here is connected to P 1.3. That is the meaning of pull up resistor. And we also know that we have a LED connected on P 1.7. So, we are going to use the available resources on the lunchbox itself to illustrate this idea of an interrupt and how an event on the interrupt or interrupt being generated by the switch can be handled with the interrupt subroutine. So, we have to include as you know this header file in our C program. We have already defined that we have a switch which is on bit 3. Now, you see bit 3 is a mask, which means what it actually is that if I have 8 bits like this, this is bit 0, 1 to 7. So, this is 0, 1, 2, 3. So, it means 1, 0 0 0 0 0 0 0. That is the meaning of bit 3, and we will use this to mask this particular bit or to do bit operations on this bit as and when required. Similarly, red is defined as a mask bit 7, that means so bit 3 actually becomes 08. So, this value is 08 in hex, and bit 7 being 1 means it is 80 hex. That is the meaning of bit 7. That is bit 7 is 1, rest bits are 0. That is the meaning of these masks. Now, in our main program, as we always do, we have disabled the watchdog timer, and we have to now tell the microcontroller that we want to use red, we want to use LED on pin 1.7. Therefore, that pin must be declared as output, and we want to use a switch on a pin P 1.3, and that must be declared as input. And so, this instruction you are deciding the direction of the P 1.7 bit as output. The P 1.3 pin is being declared as input. You are also enabling an internal pull up register by using this REN register, and then you are writing a 1 into P1 out corresponding bit, so that you are enabling the internal pull up register also. But beware that there is also an external pull up register. So, this instruction is superfluous, but it does not hurt. And then you are saying that you have to decide how do you want to generate the interrupt. Do you want to generate the interrupt on falling edge or rising edge? Since I am in the interrupt enable register, I am edge selection register, I am writing 0, that means I have chosen to generate an interrupt on the rising edge. And then on the interrupt enable register, I make that corresponding bit, that is bit 3 equal to 1, that means I have enabled the interrupt to happen on this pin. And then this instruction is used to turn the global interrupt enable bit to 1. Now, I am ready. If I go back to that block diagram, basically what I have done is here using that instruction I have turned this on, and the earlier instruction I have enabled the particular bit. Now, we are ready to do something in the main program, but the main program in this particular case there is nothing to do, and so we will simply, as you see here, we are going to wait in an infinite loop while 1. So, it is your main program is doing nothing, waiting for something to happen, and in this case that something is an external interrupt which will be generated because you press the switch on pin 1.3, port 1.3. When that happens, before that, see, you have declared that you have done hash pragma, and then vector you have said relates to this vector port 1 vector, and you have named your subroutine port underscore 1, and this is the interrupt subroutine. So, and this is the entire interrupt subroutine for interrupt being generated on port 1. What happens the moment you press a switch, and when you press a switch, because there is this switch is already pulled up, when you press a switch you get a high to low transition, and as you see here you have selected an interrupt for the rising edge. So, what is going to happen is when you press the switch, it is going to go low, this is not going to generate an interrupt, but after a while when you release the switch, this act of releasing the switch will generate an interrupt. Now, you please note here that we are calling this program a bad ISR, meaning this is not a very good style of writing an interrupt subroutine. Why? As I mentioned, interrupt subroutine must be kept short, and as you see here, we have written a delay program. As you see here, we have written a small delay program. This is not a good way of writing an interrupt, but I will explain why this is needed. Now, when the switch is pressed, it is going to go low, but as we know when a switch is pressed, oftentimes it may bounce. So, the act of pressing a switch may generate this. So, you see multiple rising edge can happen, and then it is going to be held low for as long as you keep the switch pressed, and when you release again multiple events are likely to happen, multiple rising edge can happen, and the duration of these bounces is such that the microcontroller will treat each of these bounce as an individual interrupt. Even though you have pressed the switch only once, it may interpret it that you have pressed the switch several times, and therefore, to remove that ambiguity, at this point you have waited for these bounces to die off. But what about the bouncing that may happen when you press the switch? Unfortunately, in our program we have not dealt with it, and so it is possible. Anyway, let us see what the program does. When this checks if really the interrupt happened because you press the switch. So, P1 IFG, is it 1? Isolate that bit using this AND operation. This is superfluous because since you have disabled the rest of the interrupts, this interrupt would have happened only because you press the switch, but it is a good idea. When that happens, and when will this happen? When you press the switch and release it, or if while pressing there is a switch bounce and that also generates a rising edge signal, you immediately toggle the LED on port 1 bit 7, then you delay waiting for the bounces to die down, and then you reset that flag, so that next time when the user presses a switch, it can generate an interrupt and it can execute this program. And why do we call this example of interrupt subroutine as not a good example? Is because we have used a delay subroutine. We do not recommend using delay subroutines in the interrupt program. Now, how do we deal with this? Well, make sure that you do not have to debounce your switch. Now, if the switch is read using polling, this is a good method, but reading a switch or debouncing the switch using delay in the interrupt is a complete no. So, what we do is we look at another example. In this example, we are going to use an external switch, and this is the wiring that you should do. Connect an external switch and debounce using hardware. As we have discussed in the past, one way to debounce in hardware is by putting a capacitor across the switch. This capacitor acts as a low pass filter and kills any switch bounce. So, the way this would look like is, here you have a pull up resistor, here you have a switch, and across this switch you have put a capacitor, and then this signal goes to a pin which I will briefly mention what it is. In this case it is P 1.4. So, you need to wire a switch in this configuration and connect it to port 1 bit 4. Here port 1 bit 4, you are dedicating for a new switch which you connect on the breadboard. We will continue to use the onboard LED on 1.7. Now, you see we have all the same. We want a rising edge interrupt, which means if I press the switch, it is going to go low. That is not going to generate an interrupt. When I release the switch, eventually it will generate an interrupt. And in this particular case, I have ensured by using external hardware mechanism to debounce that I am going to get a clean switch transition from high to low, remaining low for as long as you hold the switch down, and when you release it, you get something like this. And so, when you download this program, let me go back to the first program. When you compile, rebuild this program and download, what you will see is when you press the switch, if there is no bounce, you will not see the toggle of the LED, but when you release it, you should notice that the LED toggles. In case when you press the switch, the LED toggles, and when you release also it toggles, maybe it toggles multiple times, you may think that the program is not working the way it should. And the explanation of that would be that in your kit, it so happens that the switch press and release is generating switch bounce, which we are not able to deal with, at least at the time when you press the switch. For the release, we have taken care of by including a delay. And so, while releasing there will not be multiple toggling, but while pressing it is possible that it toggles when it should not. On the other hand, when you wire this external switch, there is not going to be any bouncing. Why? Because we have killed that bouncing with the help of a capacitor. Here the example is very similar, but there is no delay subroutine here, and rest of the code is very similar. You are enabling the interrupts, you are choosing that the interrupt should happen on the falling edge, on the rising edge, which means when you press the switch and release it, at that time the LED will toggle. So, please compile this program, download it in the kit, connect an external switch appropriately, and what you should observe is when you press the switch nothing happens, when you release the switch the LED will toggle, meaning if it was on earlier, after the switch is pressed and released it will turn off. When you if it is off, you press the switch and release it, it will turn on. That is the meaning of this. So, the interrupt subroutine here is a very simple piece of code which just toggles the LED. No delay instructions included in the interrupt subroutine, and this instruction will reset that interrupt flag, so that next time the switch is pressed it will be entertained. If you want to convert this program, that you want to toggle the LED when the switch is pressed instead of toggling when you release the switch, you just simply modify this part here, that you want the interrupt to be generated on the falling edge, which means when you press the switch like this and release, at this point it will toggle the LED. Rest of the instructions as you see are the same. Here you are enabling the global interrupts and you are waiting in this infinite while loop, and the only way to get out of this will be when the interrupt is generated, you will execute this subroutine, you will perform the task of toggling the LED and you will go back to waiting in that while one loop indefinitely. Now, we have a small exercise, and this would this exercise will actually help you understand that when the interrupt source is common, how do you handle that. So, we have an exercise where we would want you to connect 2 external switches and 2 external LEDs on the breadboard in the following way. Connect switch 1 to port 1 bit 0, switch 2 to port 1 bit 1. Corresponding to switch 1, we want you to connect a LED on port 1 bit 4 and another LED for switch 2 for this. And what do we want you to do? That when switch 1 is pressed and released, it should toggle the LED 1. When switch 2 is pressed, it should toggle LED 2. You can decide whether you want the toggling to happen when the switch is pressed or when it is released. But if switch 1 is pressed, it should not toggle LED 2, it should only toggle LED 1. If switch 2 is pressed, it should not toggle any other LED but LED 2. And the way to handle that would be that in the interrupt subroutine, you will have to find out what caused the interrupt. Both these interrupts are going to be routed through the port 1 interrupt, but the source is different. In one case it is switch 1, the other case it is switch 2. So, in your interrupt subroutine you have to identify which caused the interrupt, and based on that take necessary action. If switch 1 was pressed, you should toggle LED 1. If switch 2 was pressed, you should toggle LED 2, and then correspondingly clear that flag, so that that switch can again generate an interrupt. So, we would like you to write a program and test it and satisfy yourself that this is how interrupt subroutines are written and handled. Of course, we will have more examples where we illustrate how interrupts work using other peripherals of MSP430 lunchbox. So, I will see you very soon in a new video. Thank you.